Thank you. So first, I really heartily would like to thank everyone, the organizers, the foreign ones, the local ones, the staff of the ICTS, Raju. I mean, I'm loving every minute of these 2 weeks. I wish there were 2 months and not 2 weeks. So right, so I'm going to, so minimal surfaces in R4, actually, minimal surfaces for a while, is the microphone on? You hear me? Is that okay? Or okay. So, I mean, traditionally they were in R3, and then people moved on, and now they do all kinds of things. They do CMC in R3. They do. We've seen a lot of Lorentz 3 space. Also, like in Paris, where I lived for years, everyone but me and Marc Sorem was doing minimal surfaces in H2 cross R. But somehow R4, which seems like a natural place to be, hasn't aroused so much interest. So one of the things I'd like to do is sort of advertise for R4 that it's really a nice place to spend one's time. So this is joint work with Marc Sorem. We all know the definition of minimal surfaces. And in R4, there is a nice, in R3, there is a Weierstrass representation. In R4, there is actually a really nice way of representing them locally. So you have, as you know, a minimal map is conformal and harmonic. So harmonic, we all learned that the harmonic map is locally the real part of a holomorphic function. And so if we split R4 into C2, the first two components are harmonic. So the sum of holomorphic and anti-holomorphic, same for the last two components. So that's harmonic. And this is a condition for the thing above to be conformal. So this is a nice, this is a very pleasant way of seeing them. It was actually alluded to in a paper, in a 1995 paper by Micallef and White, but we've really used it more. And I talk of something local because I will be interested only in C and in the torus, but if you do this for hygiene, and you want to globalize, you need to do one form, so that obviously on C there is no one form, and on the torus there's this dz nowhere vanishing one form, so you can, it's easy. But I've been so energized by this conference that I plan to go back to Paris and start looking into genus greater than one. So so now I'm going to discuss some tools, and I apologize for people for who've seen this since they were, I mean, for whom it's trivial, who know this backwards and forwards. These tools for, I'll start with tools for minimal surfaces in R4, which are a classical, which date back from the 70s, 80s. The main names being Osserman, Hoffman, and others. But I sort of would like to put together all the information. So when you have a minimal surface in any Euclidean space, you have a Gauss map. That is, you take a point and you map it to its tangent plane, and the tangent plane lives in the Grassmannian. So everything is oriented. It's the Grassmannian of oriented two planes. So for R3, we all know what it is. It's particularly simple. The Grassmannian, an oriented two plane in R3 is given by its unit normal vector. So I have a picture like this. I have my surface, I have a point, I have the unit normal, and I map it to itself on the two sphere. And so I get a map from the surface to the two sphere, which is the Grassmannian of oriented two planes. And so it's a two sphere, but we can also view it as the projective line. And as a projective line, we have this characterization, which is extremely fruitful, that sigma is minimal if and only if the Gauss map is anti-holomorphic. So this is a question of convention, holomorphic or anti-holomorphic. So that's why I put a parenthesis. So in R4, we have not one Gauss map, but two Gauss maps, because the Grassmannian of oriented two planes is a product of two projective lines. And this is also very classical. There are several points of view, which are all equivalent. So I'm going to give one point of view, which is the one I prefer, the Ilse-Salomon point of view, which is the one I prefer, part for sentimental reasons, but also because it's the one point of view which doesn't need a frame or coordinates. It's independent of the coordinates, and which also can extend to a general Riemannian manifold by way of taking this as taking a bundle with these as the fibers. So this is the twistor approach of Ilse-Salomon. So we take a plane P in R4, and we write this matrix. We split R4 into P and P orthogonal. And then in each P, we have a rotation of angle pi over 2. So in P is angle pi over 2, and it's P orthogonal. We take two rotations, either pi over 2 or minus pi over 2. And that gives us two objects, two elements of SO4, and which verify J square. Each one of them verifies J square is equal to minus identity. And so that's a complex structure on R4. So we have these two sets of complex structures on R4. So the difference between the plus and the minus, it's a question of orientation. If you have J plus with the orientation pi over 2, that means that if I have a basis like this of R4, it's a positive basis, and J minus with pi over 2, with minus pi over 2, the same basis will be negative. I've said this is a classical and old, but still feel free to ask questions if it's not clear. So there are two, not one Gauss map, but two Gauss maps. And we have the same result, that sigma is minimal if these Gauss maps are holomorphic or anti-holomorphic. So Ilse and Salomon take the convention holomorphic, and Osserman and Hoffman and other people take more the convention anti-holomorphic. So I'll just write these for future reference. Do I write large enough?
Yeah.
So, one thing which a complex curve is like Wertinger's theorem. A complex curve in C2 is locally is actually absolutely minimizing with, and so it's a minimal surface. And you see with its description, it has one of its Gauss maps is constant. That's how you characterize complex curves in R4. So complex curve, like when you do minimal surfaces in R3, you have the planes, and the planes, they're the not intrinsic things you don't look at. And so in R4, these are the complex curves. They're there, but they're not, right. They're the non-interesting objects. So this we've seen many times. We've seen these pictures many times during this this conference. So it's just I just want to set the definitions that I'm going to consider only surfaces of finite total curvature. This is the Gaussian curvature of a surface. And for a minimal surface, it's always negative. And so finite total curvature means this, that the integral is not infinite. And I put a T here because we're going to have also the normal curvature. So this clearly is periodic, so it can't have finite total curvature. And this does. And this is the picture which we're going to keep in mind, because you see you see the ends. You see that as you go to infinity, the surface just looks like a plane. And that brings me to the definition of an end. And we've seen ends many times during this conference. So sigma is, so an end, so here you have n, capital N is equal to 1. You have just one plane. But in the general case, you have like the surface outside of a very large ball looks like a stack of flat annuli or one annulus with multiplicity n. So I'm going to also write this here. And so we have tangent planes at infinity. There is one tangent plane and one normal plane. So so this leads us to this classical construction. Sigma in R4, of course, there is no compact sigma. It has ends, but we can, because there is a single, for each end, there's a single, we can redefine the tangent plane at infinity. We can extend the Gauss maps. We can add a point for each end. So compactify sigma by adding points for each end. So we get a compact surface sigma hat. And so by mapping the point which we have added for an end, by mapping it to the corresponding tangent plane at infinity, we can extend the Gauss map to a map from sigma hat to CP1. And the same thing in R4. And so these two Gauss maps, of course, are also holomorphic or anti-holomorphic. And this is very pleasant because now we have maps from between two closed surfaces. So when we talk of maps between two closed surfaces, they have a degree, and that's going to be very useful. Questions? Right, but here I just look at the,
yeah.
I just look at the first, I don't look at what happens here. I just look at the lowest, the biggest order term.
Yes. So, but there's a difference between a planar end and the catenoidal end.
Right.
And that's not visible in the capital N.
But it's not, you don't have a lowest order, a biggest order term like XY?
Or maybe union.
I mean, I've heard these terms, but I think here I just look at the coarsest thing, that when you write the conformal, the fact that the map is conformal for a very large Z, then you get like for branch point, you write that is conformal, so the lowest order term is always Z to the power of n. But what happens elsewhere is more complicated. Right. But you're right. Actually, it has happened to me before. I talk of planar ends, and someone knows it.
Yeah, because the catenoid close like logarithm, and planar ends should go faster, right? I mean, they really go to planes.
Right.
catenoid end is not a planar end.
Right. No, but here I don't discuss at all what there is here.
Yeah.
Right. Yeah, thank you for. So okay, so we have so now we have these Gauss maps from the compactified two surface into CPN, and so we look at their degrees. So this is so again, this is very classical. The integral of the right. It's right. The degree gives us integral of the curvature, and in R4 we have a tangent bundle and a normal bundle, which is another really nice feature about R4, that we have these two complex line bundles. And so we have 2 degrees, and they give us, we have these 2 formulae. Well, actually, I'm writing, but I'm not, well, so this is the exact analog of what happens for R3 and for N. And you see, I put a minus because I have the convention that the Gauss maps are holomorphic. And here we have 2 pi G plus minus G minus. So so now we can so I've defined these degrees in terms of the Gauss maps, and now we can look at them, interpret these degrees in terms of the topology of the surface. So for so this actually, it's not just in R3 or R4. This is a general in any Rn. We have, if the surface was closed, we wouldn't have this minus n, it would be Gauss-Bonnet theorem. And so we have, this is the formula, the integral of the total of the tangent curvature is, we have this correction term, 2 pi, the Euler characteristic, minus n, the n being this quantity. And the proof is very simple. You just apply Gauss, you take your surface into a large enough ball, and you write Gauss-Bonnet, and the boundary term, this will be like, the curvature will be more or less concentrated inside the big ball. And so this will be the curvature inside the big ball. And this will be more or less the boundary term, because the boundary will be like n times the great circle. And so, right, I put this drawing again too, so you see the second and then circle. If I put it in, if the intersection with a great sphere, then the boundary is like an n circle. Here it's just a big circle. Okay, so that's, so this is, so until now, again, it was 19, I don't know, 60s, 70s, maybe a bit of 80s. It was before most of the audience was born, and now I'm doing more contemporary things. So any questions so far?
Questions?
Okay, so we had a topological interpretation for the integral of the tangent bundle, and we would like to have one for the integral of the curvature of the normal bundle. And that makes us introduce the notion of the link at infinity, which I'm going to, oh, I should have put pauses, but so I assume that the ends are embedded. And so for a large enough K, you see, for R large enough, this is my surface sigma. this is a large sphere, and so the knot is or the link is intersection of the surface with a ball, sorry, with a large enough sphere. So for large enough, the type, I mean, it's one. We'll get isotopic going from one radius to another. We'll get isotopic links or knots. And so the first, as I said here, the first approximation will just be, we have the sphere and we'll have a great circle going around n times. And when we go a bit, so I was saying to Franz, I don't look at this, but now I am going to look at the second component. So we see a finer structure, the structure of a braid. So now I look at only one end, the structure of a braid. So I don't know, maybe not everyone knows what a braid is. So I'm going to recall it. So this is, I find this picture really beautiful. It's, I found it in an article about history, a history article by someone called Michael Friedman, which is not the topologist Michael Friedman, which is Michael Friedman doing history of math. And it's a book by Artin, which is one of the founding fathers of braid theory. So you see, it's this is a closed braid. It goes, it's like a knot or a link, which there is this vertical axis, and we go around the axis. We never touch the axis, and we never go back. We can't do this. We only go in the same direction. And you can see this as actually an algebraic object. Suppose I cut this here. And so you see here, the way he drew it, what happens, most of the action is here in front of this, in this little triangle. So that's what I wrote here. I mean, it's a different braid, but that's, I don't know if you can see that here, there are colored things and black things. So the colored, so if you forget the black, the black lines, you have like these three colored strands. You see they go from, I take these 3 points, and I have 3 points here, and 3 points here, and I go from the left-hand side point to the right-hand side point by strands, which can go, one can be in front of the other, but they're not allowed to cross. And so that's an algebraic object, and and these objects belong to a group, and you can really do algebraic computations. So so now I'm going to define the rise at infinity, which this is the not so pleasant part of the talk, because it involves doing a drawing with several colors and drawing R4 on the blackboard. So okay, so first let me I have the drawing on the slide, but I think it would be better understood if I draw it step by step. So I have my I have my surface. I have my sphere. So it's actually not at all realistic. Yes. Oh, okay. I thought you were going to protest that it's really not real. I mean, feel free to protest. I mean, you. So as I said, this is the knot, and so at infinity, I have this. I have like the tangent plane at infinity, and I have a normal direction at infinity, and so this I push it in this direction, in the normal direction. So it stays on the sphere. I mean, but so I get k, or maybe here I called it gamma. Right, okay, sorry. So I have gamma, I get gamma tilde, which you believe that it's still in the sphere. So this is gamma tilde. And I take their linking number. And that's the right at infinity. And I claim that this linking number is exactly the, oh, I'm sorry, I forgot the 2 pi. Yeah, that's the problem with slide stock, that you, even if you read it at your desk a zillion times, it's only when it's on a big screen that you say, oh my God. So I'm going to write it here.
Marina, may I ask, is that the X, is that you have a two-dimensional normal space in R4?
Right.
And so you choose any normal, or do you choose a normal in the 3?
Well, this is right. This is the part which I was sweeping under the rug, because the it's like a great, the link is, the knot is like a great circle. When you push in the normal direction, you're almost you're sort of, at first you're tangent to the sphere, so you just move it a little. This is not because the knot is actually more or less included in the tangent space at infinity. So when you push and you're more normal, you're also normal to the knot. So tangent to the sphere, and indeed you're not. The sphere goes like this, and you push like this, but you arrange it right. So I'll give you. I mean, it's. I'll sketch the proof, which is not complicated. So I have. So here I have my. This is my normal vector x, and I extend it to so it's normal at infinity. I extend it to a normal vector, to a vector which is normal to the surface, and then I say, okay, I want to compute the total curvature is just like the amount of normal curvature inside the ball. And so it's, since I now have this vector space, it's equal to the number of zeros of this vector field plus a boundary term. So the boundary term, it's okay. Oh, sorry. No, I'm sorry. So the boundary term is not important. So it's just, so we just have to compute the number of zeros of this. And actually, there is a fact that when you have two knots on the 3 sphere, which bound 2 surfaces inside the ball, their linking number is equal to the number of intersection points of the 2 surfaces. So now I push my surface in the direction of xn. And then the number of zeros will be exactly the number of intersection between this surface and the new surface pushed. And this in turn would be equal to the linking number between the two knots. So I'm sorry, it's very simple. I'm sorry, I was a bit pedestrian. So and so when you have a single end, remember I said we can draw the knot at infinity as a braid, and so it turns out that it's what we call the algebraic length of the braid. You see, you have a braid, and you have the intersection points, and you give them a sign. You say this point would be, we give it a sign negative, and this point would be positive, and so we count the intersection, we count the number of intersection points of this braid, and that gives us also the right at infinity. So this quantity actually appears in Joel Fine's work. Joel Fine is doing something really interesting. He's taking surface S3, and for which is a boundary of H4. He's taking a knot. He's building invariance of knots. So he's taking a knot in S3, and he's counting the minimal surfaces bounded by this knot inside H4. And so he did this for the disks, and now he wants to do it for more surfaces. And so he wants to have an invariant where he fixes the genus of this, and also the rise at infinity, which he gives a different name, but it's the same notion. And connecting back to Ilsen and Salomon, this is very interesting because these minimal surfaces actually give him pseudo-holomorphic curves in the twisted space of H4, which it happens to be symplectic. So I'm doing more name dropping because it's not my field, but it's very interesting work. Right, so now question, which knots do we get? So I'm not going to get into that. I just want to show you one kind of knot which appears in these knots at infinity. So, so we have the end, and every term of biggest order in every component is a harmonic function. I mean, the components are harmonic functions. So every biggest order term is like real part of ZP, imaginary part. Here we have a phase, but it doesn't matter. And so the favorable case is that when you can only look at the red terms, if we truncate and we just look at the red terms, the biggest order terms, we have an injection. And so that defines a knot. And this is, there are other knots. This is a basic example. And we called it, there's a phase to prevent the knot from being singular, but it doesn't change the type of the knot. And so what are these knots? So first case, Q is equal to P, then it's a torus knot. So this is from the knot atlas. So the torus knot in R3, you take a vertical circle, you go around it Q times, and while you go around it Q times, you rotate it N times around the vertical axis. And so when Q is different from P, we have something similar, but instead of a circle, we have a Lissajous curve. A Lissajous curve is a curve which has components to a trigonometric function. So so our parameter moves around this curve, and this curve is vertical. And while it moves around this curve, the curve is rotated around the z-axis. And so this is just an example. We got into these kinds of knots when we were looking at branch points, and we were trying to see what are the knots defined here. For the branch point of a minimal surface, instead of taking a very large sphere, you take a very small sphere, and you have a knot. And with Marc, we were trying to see, we get all knots, and 20 years later, we've sort of given up. So I don't know. But anyway, this is a nice class of knots. Questions? So now I'm going to, I know the title contained tori, and I see the tori part will be only 15 minutes, but I still want to talk about before tori. We have a simpler example, which is just minimal planes. And so minimal planes in R3, this is trivial. If we take a proper, complete, minimal conformal embedding of C into R3 with finite total curvature. So all these assumptions they're valid throughout my talk. I mean, it takes 2 lines to state them, but that's the objects I'm looking at during the whole hour. So you only have the Euclidean planes. And so the question, so of course you have many immersed examples, and there's the upper surface, which we have seen several times during this conference. So I didn't say, but none of the, I mean, the pictures of the surfaces are, in case you had not guessed, they're not, I didn't draw them. I mean, they're either from Wikipedia or from the Weber's very, very nice website. So the upper surface, which has this end, and then like this. So even though we can view it in we can view the upper surface in R4. So instead of just the thing at infinity, instead of being in the full R, I mean, will be in an S2 inside S3. And so we can draw the braid at infinity. And of course, it would be singular, because the braid, think of the braids I showed you were sort of 3-dimensional. They were on the plane and apart, orthogonal to the blackboard. And this is 2-dimensional. And so maybe I should explain to you how we get these braids and the connection between this formula and these pictures. The knot at infinity, we parameterize it by theta into 0 to pi. And so we go, when we have the Z3, we do exponential I theta 3 times. This component goes 3 times around the knot. And so we have, we split the interval for each of these intervals. We go around the knot once. You see I go, and so what happens in R4? So what are the embedded, are there embedded minimal planes in R4? So there's a trivial example of holomorphic of complex curves. And, but they're not the only ones. I mean, by analogy with R3, we could have thought they're the only ones, but they're not. So for example, we can desingularize the upper surface by adding a fourth coordinate. And then we get this braid a knot at infinity, and it's a trivial knot, and it's embedded. On the other hand, we can desingularize the upper surface in a different way, and we can get this. Well, this is a complex curve, of course. And then the knot at infinity is this knot. It's a trefoil knot. So the trefoil knot we're used to seeing differently, because we used to seeing it as a 2-3 torus knot. It's actually the 3. Here's a 3-2 torus knot. So we desingularize it differently. And but here there's a double point. And we have an example of another example. So it seems to me this is one of the, I said in the beginning that R4, I think, has been neglected. This question of what are the minimal embeddings of C into R4? It seems to be super basic, and we sort of don't know anything. So we have a project with Pierre-Vincent Kozelek. We reduce we have candidates for embeddings, and we reduce the problem to algebraic equations with Chebyshev polynomials, and you have to solve them, but we have not solved them. We have, okay, so now I'm finally going to, after this 40-minute long introduction, I'm going to start the topic of my talk about tutori. Are there questions? Okay, so just to set the notations, a torus is a quotient of a complex plane by a lattice. So the lattice, we normalize one component, one quantity to one, and the other one is tau. And so different taus, tau with strictly positive imaginary part. So different taus can give us the same torus. So we have a moduli space of the two tori, which is the thing which is shaded in red. So this is a plane. And for each point in this region, there is, for tau being each point, there is a single one and single torus with this tau. So we start with R3. What do we have in R3? So in R3, we have some examples. They're all on the square torus. The square torus is here where tau is equal to 1. So it makes sense. It's the fundamental domain is a square. So with the Costa torus, which is embedded, which Barbara mentioned. And we have this Shen-Gaxteter. It has one end, curvature minus 8 pi. And the end is the same as the n-upper surface. And Weber and Lopez have independently shown that for the square torus, that it's the only minimal torus for minus 8 pi and curvature minus 8 pi and one end. And so what do we do in R4? Can we do what we did for the n-upper surface and desingularize it?
Sorry, I have a silly question. So these are puncture tori.
Right.
So how do I identify?
They're puncture, and each puncture corresponds to one end.
Right,
Each puncture gives us
but then the previous picture was the moduli space for closed. I mean, like.
Right. So the result will be we take a torus like this and we give it one puncture.
So for in the puncture torus, you could figure out which closed torus the conformal structure.
Right. We will actually have in practice we will have like a fundamental domain, and here we'll have 0 and we'll puncture in 0.
I thought putting a I thought more punctures would make the dimensional modulus bigger. Okay. I could ask you later. I think there's confusion on my part.
So
back to just to make sure, because no, the other one, the next slide. So Shen-Gaxteter is the only one-ended minimal torus,
minus 8
but
pi.
with minus 8 pi.
Right, and for over all conformal.
No other conformal type is possible.
Right.
And so this is n-upper surface with n.
Right, the ends are n-upper surfaces.
So what n-upper has 4 pi, right?
Right.
And then the handle adds another 4 pi.
See, you can write. Should I write it or the you have this formula. So for the Shen-Gaxteter and the n-upper torus and the n-upper surface, n is equal to 3. So for the sphere, for the n-upper surface, you have that will give you 2 pi. So the curvature of the plane, 1 minus 3. So this is minus 4 pi. And for the torus, you will have 2 pi. So this is, you have the torus, which is 0, and you remove 1 point, you get minus 1. And that gives you minus 8 pi. Thank you for asking, because I wondered if I should do exercises about the formulas and then.
Then I don't quite understand your question number 2, because didn't you just say that?
In R4, this is in R3.
Oh, I see. Okay, sorry. Yeah.
Right. Right. In R3, there's nothing outside of the square torus. Can we have that in R4?
Hexagonal one, do you get? You know, the one which is the hexagonal lattice.
Right.
In R4, is that?
Right. But if it's hexagonal,
Sorry?
if it's hexagonal, how is it?
Do you have an example? My question is, do you have an example of a hexagonal structure?
No.
No?
But that's actually, you know what? That's actually the, maybe,
Hexagonal would be on the, you know, where the vertical line hits the circle.
right.
That's the hexagonal, 60 degree. You don't have one of those.
No, because I actually didn't construct them by gluing fundamental domains. I constructed by sort of brute force writing the coordinates. But actually, I was thinking that's no. I want to hear more about this. I mean, that could be the next tool. So, right, so first the algebra is, as I said, is always the algebraic curves as an example. And so this is a result which is, as you will see, and as you see from me answering questions, is extremely partial. So this is the moduli space of the tori. So on the square torus, this is the only, so we look for things minimal tori with one end and total curvature -8 pi. So the square torus is the only case where we have a complete answer. We desingularize Schoen-Gaxteter, and we have, okay, so it's in dimension 4. We don't have a codimension 1 singularity, but we still have double points. And then this is the vertical axis. I don't know if you can see, but I drew it in green. Because this is a rectangular tori, so which means the fundamental domain is a rectangle. And so we have explicit solutions for every R. And actually, I'm so sorry, when R tends to 1, they do converge to the square torus solution. That's really bad. You have the Schoen-Gaxteter torus in R3. And you can deform it into Schoen-Gaxteter tori in R4 while staying on the square torus, or you can deform them by these rectangular tori in R4. So I'm sorry, and this is not a typo. This corresponds to 2 stages of at first, we really thought they did not converge, and then we realized, no, they do converge. But still, I mean, I shouldn't have it. So they do converge. Maybe actually I can send a corrected version of the slides after the, okay, and so we have one non-existence result, which is this one, equi-anharmonic torus. And there's an I lacking. It's tau is equal to exponential 2 pi over 3i. And elsewhere that we don't know. So you see it's really, really partial. And clearly to get more results, we will need more techniques because this is, I think the techniques we used here have exhausted their usefulness, unless I really want to spend the next 20 years. So we do it. Remember, I said the minimal surface. I didn't write it. Remember, in the beginning of the talk, I said the minimal surface is constructed locally like that. So we're on the torus. We can actually look for global holomorphic functions like that, or rather meromorphic with a single pole. So we look for these two functions, for these four functions. And so we look for meromorphic functions on the torus, and the building blocks of meromorphic functions on the torus are the Weierstrass P function, and Rahul you mentioned it. And so it's this function which is doubly periodic on C, and P prime are the building block. All meromorphic functions on the torus are building from P and P prime. So I wrote tau in red because I wrote in red the parameters of the equation. So there's this nice identity, which I'm writing this to introduce G2 and G3. Okay, there's this identity, and I think it's very nice. It's very meaningful because you see, this is aside. This is not something I use for the proof, but general culture aside, you see this is a cubic equation. So this actually gives us the connection between the torus as a quotient bilattice and the torus as a cubic curve in a cubic curve. So we have these. So when we will construct these, we'll have already three parameters: tau, G2, and G3. And so we write all these equations. We write these. We look for functions which are combinations of P squared, P prime, P, and a constant. And we write this equation. So that gives us a slew of equations. And then we have the period problem, because this is doubly periodic, but we're going to take the integral of this. So we want this to be we want these periods. Right, we want these to be well defined. So we want these integrals along the two sides of the fundamental domain. We want them to be zero. So it's a period problem, which is a very classical problem for everyone who does minimal surfaces in R3 or 4. And so that leads us to another parameter. It's another well-defined quantity, the integral of P on the side on one of the sides here, for example, this one. I don't use the one of the integral on the other side because they're a function of one another with a very easy formula. So to summarize, I have, and so here you see there is bars. So the equations which we will get with these quantities are much less nice because these are just complex equations. We could say, okay, there are so many equations, so many unknowns, the space of solutions has this. But here we have conjugates. So what we end up is having, all these equations in all these quantities with these four parameters, tau. I mean, they all depend on tau, the four parameters, tau, G2, G3, and eta 1. So these are enough to show us. Remember, I said there is no, we have a non-existent here. So this massive system of equations is enough to show the non-existence. But to show the existence, we need to make our life easier. So that's why we do rectangular tori, because the rectangular tori, so tau is equal to I, and all these three quantities are real. So this really annoying problem that we had numbers and conjugates goes away. So that's the rectangular torus is not, it's just that it was easier to do. It's not that it has anything special. So we work on the rectangular torus. We also do an extra assumption which will make our lives easier. And we end up with, so we started with 11 equations. No, hold on. 10 equations with 11 unknowns. With a bit of work, we brought them down to 4 equations with 5 unknowns. And once we are in the rectangular torus, we brought it down to a single equation to have something. I'm just 2 words. We have an equation like this: x squared is equal to sort of massive expression. And we just need to show that the massive, but x is now real. So we just need to show that the massive expression is positive. So we do that with Sage Math helps us. And we do estimates and anyway. But so we eventually find actually a really explicit solution. We can write each coordinate explicitly in terms of R. The expressions are not difficult. And then maybe they're not embedded. I mean, the whole point, when we started this project, the whole point was to find embedded tori. And now it's a sort of the worst possible situation. We don't even know if they're embedded or not. So the knot at infinity, when you, asymptotically, when you make, it looks like this with a singular point. But it's asymptotically, so we don't know. We can't say it's embedded. We can't say it's not. So it's frustrating, but okay. So thank you.
Any questions?
You have, okay, so you talked a bit about knots at infinity. So like, is there a, I mean, I know that this is some sort of a general question, but like, is there some sort of a well-developed theory in it? Because I think that it will be substantially, I mean, it will be somewhat different from the regular knot theory, as in that you have stuff like the Jones polynomial turning out to be related to the Chern-Simons theory, which very well it depends on the compactness of S3, and I do not think that this will work in this case.
I'm not sure I completely followed. I'm sorry, can you say it again, please? I'm not sure I completely followed what you said.
So can you suggest some references for knots and links at infinity?
Right. So the links at infinity, what?
So how do they differ from the regular knots or links embedded in R3 or S3?
The links at infinity are in S3? Sorry?
No, I meant in the sense that how does, I mean, how do they differ from the knots that we have in R3?
Oh, how do the links at infinity differ from what in R3?
Links in R3.
Oh, okay. Oh, I'm sorry. Of course, well, actually, the links in S3, S3 is just R3 with a point at infinity. So the theory of links in R3 and links in S3 is the same. Was that your question?
No, I was asking about whether is it the same as the links at infinity, which you have mentioned sometime before in your talk.
Right. If they were immersed, if there are cases where they're immersed.
Yeah.
Right. Okay. So yes. So for the NPR surface, they're immersed. I mean, they have isolated double points. If the surface has a codimension 1 singularity near infinity, then the link at infinity will also be immersed.
Yes.
Was that your question?
Yeah, sort of. Thanks for answering it.
Maybe when we see each other in person, we'll,
Mm.
we'll
Okay,
talk
so
better.
I wanted to ask something a bit different. So, do you think, have you looked at the possibility that you pick a rectangular torus that's not the one on the bottom, but just one of the, any of the rectangular tori on the half line, open half line?
Right.
Could you try to prove that the space of tori for which there is an example would be open?
Oh, we have,
I know you've got an open line, but it's not open in the moduli space. So try to prove that there's like a little disk by some kind of linearized analysis. So you linearize the minimal surface.
so you're,
You've got this line.
so you're not talking about this.
No, I'm talking, when you drew the picture of the existence and non-existence, you go back.
Right.
If you go further along.
Right.
Yeah, here. So you see that you've got this green line where
Right.
you know there's an example for every point on the green
Right.
line. I'm asking, take a point on that green line, so not the blue point. So any point on the green line, linearize this minimal surface problem and try to see, does that problem always have a solution, even directions at right angles to the green line?
You mean like a minimal implicit function theorem?
Yes.
Yeah, actually, I tried doing this. Yeah, I tried doing this, and then yeah, I should retry again. Yes, thank you. No, I tried, and I think, I mean, in version point something, around this green line, there was a little shaded zone in a different color because we had an implicit result, and I don't remember why it's not there anymore. Yeah. Speaking of implicit functions, there are two people, Xia and Ma, who who looked at this problem in R31, and so they did an implicit function approach around the Schoengack-Stetter, and they got implicit tori in a little neighborhood of the square torus in R41. No, 3.1.
Are there any questions?
Okay, this is about embeddedness. Okay, so you don't know embeddedness, but even not in the compact part of it, it's just is a problem at infinity or is a problem everywhere?
I think it's a problem everywhere. I mean, at infinity, it should be easier because at infinity, you can, if the largest order terms are embedded, then you could say everything is embedded. But but in the middle, it's just impossible. You have equations. You look for the double points, and you have equations with which makes Weierstrass function, their conjugate, constant. So,
okay. Right. So the problem is more in the compact.
Right. Right.
Thank you.
Oh, no, I think it's in the, it has, it's a, inside the fundamental domain, it has a double pole. Right, but double. So it's like two, right. an analog of I think there is. I think Mark found a book by Aminov. And I think he's, right. What, is it? We haven't, right. Because actually these four functions, they're actually really nice. And for example, one other nice aspect of these four functions is that the two Gauss maps, they're just a quotient. One Gauss map is minus f prime or plus or minus, and remember, f prime 1 over f prime 2, and the other one is f prime, no, f prime 4, and the other one is f prime 3 over f prime 2. So they're very pleasant. But it's possible that now to go for genus greater than 1, it's very possible that this will not be enough, that we will need, right.
Rukmini, to your question, there is this representation by spinors. And that's Taimanov has written on that, and Konopelchenko. But also, I mean, in this quaternionic theory, which I was once doing many years ago, there's a nice minimal surface represent. That's exactly what you ask. And you solve just a del bar problem. Well, that's what you ask. What's the Weierstrass representation? It looks very simple. I mean, you have two complex spinor fields, so sections of spin bundles over your compact surface, say, when they're meromorphic sections, because you have, you must have ends, and then the formulas are just like you expect them. That sounds like spin up psi1 squared plus psi2 squared is the first entry, and then the other one is over psi1 squared minus psi2. Very, very simple formulas. Psi's are either you can think of them complex valued in a trivialization or bundle valued, and squaring is the spin pairing. So there's actually a nice, I mean, I don't want to self-promote, but there's an ICM article where we worked this out, and it was once an ICM a while ago. I forgot when it was, 98, I think. But Taimanov, Konopelchenko are good references for that.
Actually, I wonder if it's not the first time when I met you, I think at IHP, you gave, it must have been 99, and you gave a talk about this quaternionic.
Could be. Yeah.
Right.
Right. Other question I had, you are linking or with the number, is there any relation to the normal bundle degree, or is this completely?
Oh, yes. Oh, I'm sorry. That, yeah, the rise at infinity.
Yes.
Right. No, absolutely. That's that's why it's interesting. You have it's 2 pi, right? The rise at infinity. This if it's embedded, and if it's not, if it is not embedded with a transfer double point, you have minus 2d. And so this is a tool to check that it's the thing, something is not embedded. For example, I mean, if you, for example, if you look at the torus, so the torus, the Gauss maps are maps from the torus to CP1. So the degree is at least 2. So you have, in this situation, d plus greater or equal to 2, d minus greater or equal to 2. But if you assume curvature minus 8 pi, you have d plus d minus is equal to 4. And so then that with this, you have d plus is equal to d minus is equal to 0. And so the curvature of the normal bundle is 0 in our situation. And so if the rise, so for the Schoengaxeter desingularized, the rise, since the link at infinity is a torus node, so this is not zero. So here we see that it's not embedded.